All right. Okay. So I'm going to apply the regular input network here. This would represent INN, our input referred noise current. Here we're going to have VNN, our input referred noise voltage. And usually, we would apply our input signal here. And all of the input signals that we've been dealing with to this point have not had any associated source resistance. So let's make that happen by just having some generic impedance ZS that would be associated with the input stage of our amplifier here. Okay. So because we have a transistor M1 here and a resistance here, right? Each of the transistor and the resistor are going to generate some noise. So for transistor M1, we know that we could have a noise source here, which I'm going to call INM1. And similarly, for our drain resistor here, I'm going to say that I have some current INRD. And based on the results of our last example, and we can walk through this real quickly if you want to. Obviously, there's going to be some total noise current at the output that is going to flow through that resistance RD if we are neglecting the output resistance of the transistor itself. So that we would wind up having VN out squared is equal to IN total squared times RD squared, which gave us, 4 KBT gamma GM plus K GM squared over Cox WLF plus 4 KBT over RD. All of this multiplied by RD squared. So to be real clear, actually, let me lump these two guys together. This is the contribution from the transistor. This is the contribution from the resistor, where our transistor has both thermal noise, which is a bit with the 4 KBT out front, as well as flicker noise, which is the divided by Cox WLF bit, right? So as a result of this, we found that VNN was 4 kBT gamma over GM plus K divided by Cox WLF plus 4 kBT over GM squared RD. This is what we did when we found the input preferred noise voltage for the last circuit. Where I'm going to call this bit right here VN M1, and this bit right here 1 over GMRD squared times VN RD. So we have an input referred transistor noise and an input, or we're breaking up our total input referred noise into an input referred transistor noise and an input referred resistor noise, right? So we get from VN out to VN in just by dividing by the gain squared. Okay, so that's the only difference between these two guys. And give myself a little bit more room over here. Actually, let's take one more step here. I can say that VN in without the squared bit, so my voltage spectral density isn't power, it's going to be VN M1 plus 1 over GMRD times VN RD, and I'll explain why I'm making this distinction in a moment. From our last example problem, we also saw that our input referred noise current, IN was SCN squared times 4 kBT gamma over GM. Let me make that gamma look more like a gamma. Plus K divided by Cox WLF plus 4 kBT over GM squared RD. And so this bit is associated, or actually, this is exactly what we've defined to be VN M1 squared. And this guy right here is exactly what we've defined to be 1 over GMRD squared times VNRD. And from this, we can say IN, our input referred noise current spectral density, is SCN times VN M1 plus SCN over GMRD VNRD. So I'm putting both my input referred noise current and my input referred noise voltage in terms of these measured output noises that we've referred to the input. Okay. All right. So since both of these input referred noises depend on the same quantities, VNM1 and VNRD, we have to assume that they're correlated, right? They're of the same basic form and all that kind of stuff. They're just scaled by different factors, okay? So because they're correlated, we can't simply add their powers at the output. We need to apply direct superposition, okay? In order to find out what the combined noise voltage at the output is, right? We're trying to see whether or not we're counting this thing twice. So with VS on, and our current source off, what we have is this circuit. Here we have RD. Here's our output noise voltage. Here's our capacitor CN. And all I'm doing here, I'll go back and show you. Let me circle back around to my original drawing here real quick. This guy right here, okay? So I'm turning off my current source, which means I replace it with an open circuit, right? I'm using the superposition principle. So I see that ZS, my source voltage, or excuse me, my source impedance from the actual input stage is in series with my noise voltage generator VNN. So I'm just changing the order in which those two appear in the circuit, but because they're in series, I'm free to do that. It's just gonna make the math slightly easier to understand. Okay, so that's what the difference between this guy and this guy is. I have turned off my current source because I'm applying superposition, and I've just swapped the order of my input noise voltage with that source impedance so that I can see that I have a pretty simple and straightforward voltage divider circuit at the input of this guy, which is going to make it much easier to figure out what the output caused by this input noise is. So if I call this voltage here Vx prime, I can see that Vx prime is equal to Vn in times 1 over SCN divided by 1 over SCN plus ZS, which is the same as Vn in multiplied by 1 over one plus SCN ZS. So I'm just multiplying through by a factor of SCN over SCN to get rid of the fractions in my numerator and denominator. From here, let's call this Vn out single prime because it's only the contribution of the input referred noise voltage. So this is a common source amplifier acting on some input signal Vx prime. So I'm going to multiply this signal by GMRD. I understand that I should actually be multiplying it by negative GMRD, but again, we're playing fast and loose with signs because we're dealing with noises, which are random processes here. And so substituting in Vx, this now becomes Vn in times 1 over 1 plus SCN yes multiplied by GMRD. So that's the contribution with just my voltage source on. With my voltage source off, and my current source on, my circuit's going to look like this. Here's RD. Here's VN out double prime. Oops. There we go. Here's my capacitor, Cin. My current source is now on. So this is IN in, and here's my impedance, ZS. And it's showing up between this terminal and ground, just to be clear here. Because when I'm doing a noise calculation, oh, well, actually, I don't even need to explain it that way, right? I'm just turning off that input voltage source there. I turn off a voltage source by replacing it with a short circuit. So this is what I have. I'm going to call this voltage at this gate node Vx double prime. And I can say that Vx double prime is equal to IN multiplied by those two impedances in parallel, right? So that should look like Vs over SCN divided by Vs plus 1 over SCN, which is going to be IN let's see, multiplied by ZS divided by 1, why is this being difficult, plus SCN. Yes, I've cleared my fractions correctly. And from this then, Vn out double prime, just Vx double prime multiplied by the gain, GMRD, which looks like IN multiplied by ZS divided by 1 plus SC and ZS multiplied by GMRD. So I have the contributions from the circuit operating with both sources on. So now we apply the additivity principle of superposition and add the results together, right? So doing that here, we can say that Vn out is equal to Vn out prime plus Vn out double prime is going to give us Vn in times 1 over 1 plus S Cn ds times GMRD plus IN in times ZS divided by 1 plus S CN ZS times GM RD is going to look like VNN plus ZS multiplied by IN in divided by 1 plus SCN ZS. This whole thing multiplied by GMRD. Everybody okay thus far? Now we're going to have to start doing substitutions. So I'm going to pull out, I'm going to, I guess, slightly rearrange the way that I'm expressing this. So I'm going to pull out GMRD over here to the front, and that 1 plus SCN ZS over here to the front. So when I have VN in, that was VN M1 plus 1 over GMRD times VNRD. ZS times IN is ZS times S CN VN M1 plus ZS times SCN over GMRD multiplied by VNRD. And grouping alike terms, I have GMRD divided by 1 plus SCN ZS multiplied by 1 plus SCN ZS VN M1 plus 1 plus SCN ZS divided by GMRD times VNRD. So this guy and this guy are a common factor that are canceled out by this denominator here, leaving us with GMRD times VNM1 plus 1 over GMRD times VNRD. And from this, finally, we can see that our output power spectral density is GMRD quantity squared times, substituting back in our definitions for VNM1 and VMRD, 4 kBT gamma over GM plus K divided by Cox WLF plus 4 kBT over GM squared RD, which is the same as 4 KBT gamma GM plus K GM squared over C ox WLF plus 4 KBT over RD multiplied by RD squared. So effectively, all of this was to say that if we break this down using superposition, apply both of our input referred noise signals individually, and then using superposition, add the results together at the end, we see that we get the exact same result as if we had just done the original, or we get the exact same result as when we had originally determined our output noise, right? So both of them lined up contributing. I mean, this is in the extreme case, or not really an extreme case, in a general case where we don't know what ZS was, right? So it could have been anything ranging from an impedance of 0 ohms all the way up to infinity ohms, and it's valid here. So we're not counting the noise twice by referring, having an input referred noise voltage and an input referred noise current. The contribution of each one depends on what that, or to the output noise, depends on what the impedance ZS is, right? So when ZS is a short circuit, effectively all of the current noise gets sank to ground right out the gate, and all of the output noise is due to the input referred noise. On the opposite end of the spectrum, if ZS is infinitely large, none of our voltage noise gets transferred to the output. It's all due to the current noise of the input. All right, so that was an ordeal. Let's put this into practice with an example problem or two, okay? So we have beaten the common source, I keep saying source because I'm anticipating saying the word noise, common source amplifier to death. So let's look at a common gate amplifier. So here we have some resistance RD. Here's V out. Here's our terminal where we apply our input voltage. And let's say that we have RG here and some biasing voltage VG here, right? So this is our amplifier where we are assuming that this guy is biased in such a way that it's operating in a saturation region and all that kind of good stuff. We're going to analyze this guy with CLM and body effects ignored, just to make the math slightly less of a pain in the butt. All right. Our goal here is to figure out what VN in is and IN in. So we want to figure out what our input referred noise voltage is and our input referred noise current is. So using our previous examples as kind of a step-by-step guide for what we should be doing here, the first thing that we are going to do is we are going to take this circuit, model the noise by our two resistors and our transistor, turn off our input entirely, right? So we turn off our input source voltage and then just see what noise is generated at the output, because that tells us how to refer things to the input. All right. So step number one, determine VN. So for our circuit, we know that our resistor RD is a white noise generator, and I am choosing to represent that with the parallel representation, a noise current in parallel with the resistor RD. We know that our transistor M1 is both a thermal noise and 1/F noise generator. I'm going to call all my transistor noise INM1. That should be connected between the source and the drain. So this is the source. Sorry, that's not remotely the source. Drain, source. And then we have some resistance RG here. And I'm going to choose to represent this noise voltage generated by resistor RG as a series connected source. And my output signal here, VN out. So let's talk about some of the decisions that I have made here. Okay. Choosing to put the noise from resistor RD in this configuration makes it obvious that I can add it as being a current source in parallel with the noise from the transistor, which is what we've been doing in all of the previous examples. So that's just kind of making sense there. All right. Now, the noise voltage that is generated by our resistor RG, I'm drawing it explicitly here because it might be less intuitively obvious that we can refer that as a noise that will wind up being between the drain terminal and ground, right? So with this configuration, we have to think about how this noise is going to contribute to that output noise, right? Anybody have any thoughts? Whole goal of this transistor here, if we work this thing with all of the other sources turned off, this is serving as our input voltage for this amplifier, right? So it should make sense that if we're not worried about the drain resistor noise and we're not worried about the transistor noise, this noise will get converted into a current flowing between the drain and the source, because that's exactly what the transistor does, is converts that input voltage into a drain current. That drain current will then flow through that resistor RD, generating some output noise. So all of this to say, our total noise current that we'll see flowing from the drain to the source, which is at ground, is INRD plus VNRG multiplied by GM squared, right? That's me referring that noise, converting that noise to a current that's flowing between the drain and the source, plus IN M1. And then just substituting in our values here, this is going to look like 4 kBT over RD. That's my noise current spectral density for resistor RD. Then I'm going to have 4 kBT times RG, which is my noise voltage generated by my resistor RG, multiplied by GM squared, which is converting it to a current at the output side of things. And then to this, I will have add 4 kB T gamma GM, which is my thermal noise from my transistor. And I'm running out of room here, so let's say that we ignore the 1/F noise. Let's say we're working at a frequency where it's not going to matter, just because I'm running out of space on the page. Okay. So with CLM, and let me change this slightly. Body effects and 1/F noise neglected. All right, so we know what our output noise current is. How do we get our output noise voltage? Well, if we look at our small signal model with all of those noise currents lumped together, we can see that our gate terminal explicitly is grounded. Here we have resistor RG. So this is going to be our voltage VGS. Our source terminal for our transistor is grounded. Here we have GM, VGS. Since our channel length modulation is ignored, we won't have that resistor R out to worry about here. So I'm going to put this guy in. So this is IN in, or excuse me, IN total. Here's our resistance RD between drain and ground. Here's our output noise, VN out, that we're trying to find. So we know that this guy contributes no current because VGS is exactly 0. So that means all of our noise current only sees that resistance RD. And so from that, VN out squared is equal to IN total times RD squared. Which is going to be 4 kBT over RD plus 4 kBT RG GM squared plus 4 kBT gamma GM all multiplied by RD squared. Everybody okay with that? All right. So now the easy step, or probably the easiest one in the whole problem, figuring out what the input referred noise voltage is, right? So the input referred noise voltage, let's call this step 2. The input referred noise voltage, VN in, is always simply Vn out divided by the voltage gain of our system squared. The reason why this part is so simple is because we are so used to dealing with voltage amplifiers, where we have a simple input voltage, output voltage relationship that's been classified by our amplifier gain, right? We don't have to do any real extra work here as long as we know what the gain of our system is. So what's the gain of our system? Or what's the magnitude of the gain of our system? So this is a common gate amplifier, right? Anybody remember? Let's start there. Nobody remembers. Okay. No. All right. So since we don't remember what the gain of our system is, I wasn't expecting to have to do this, but that'll be okay. We can figure out what the gain of our system is pretty easily, right? So draw our small signal model. We're going to come back around to this guy here. We know that our gate has that resistor RG applied there. Here's our gate terminal. Here's where VGS occurs. Here is our source terminal. Here is our dependent current source, GM VGS. And so since we're trying to find our gain, we no longer consider the source terminal to be grounded, right? Because if we scroll up here, way back to our original circuit, the source terminal is where we're applying our input signal. So my input signal still needs to be applied at the source. So here's where Vn is, and my resistor Rd is placed between the drain and the ground. I'm trying to find this voltage, V out. Everybody okay with what I've drawn here? Small signal representation of this basic amplifier circuit, exactly what we did back in, I think, 335. So it's fairly obvious that V out is going to be negative GM VGS times RD, because we know that a total current of negative GM VGS must be flowing down through resistor RD, which is generating our output voltage. So we need to figure out how to relate one of these quantities to Vn to figure out what our gain is. Well, obviously, the transconductance doesn't have anything to do with the input voltage. The size of our drain resistance, RD, doesn't have anything to do with our input voltage. So our only option here is to figure out how to express that voltage VGS in terms of Vn. Anybody have any thoughts? Exactly right. VGS is equal to negative Vn by inspection, right? So the negative polarity terminal of VGS is associated with the positive polarity terminal of Vn. The positive polarity terminal of VGS is associated with ground. The negative polarity terminal of Vn is associated with ground. So those voltages have to be the exact same thing, but of opposite polarities. So that's why VGS is equal to negative Vn. And putting these two things together, then we find that AV is equal to GM RD. So if we divide this guy by GMRD, quantity squared, what happens? Well, the RD squared gets thrown away and all of these terms get divided by a factor of GM squared, right? So that means that our input referred noise voltage is just going to be 4 kBT over GM squared RD plus 4 kBT RG plus 4 kBT gamma divided by GM. Everybody okay with that? All right. So this is actually potentially informative here. And the reason why I say that is because hopefully it makes sense as to why we're just dividing the output voltage by the output noise voltage by the voltage gain squared, because the voltage gain here represents the transfer function of this system, converting that input voltage to an output voltage, and so it should go the other way around as well, right? When we find the input referred noise current, we're actually doing the exact same thing, except that we're no longer using a voltage gain, we're using, I guess it would be trans resistance gain, because we're converting an input current signal, that noise that's generated at the input, or the input referred noise, and making it match the, and converting that noise to an output noise voltage, right? So with that conceptually in mind, think about what we would be doing here, all right? Determine IN. Okay. So if we take our original noiseless circuit, here we have VDD, here we have RD, here is our output voltage V out. Here we have RG. I'm going to call this guy, for the sake of argument here, an AC ground. Now I'm applying a noise current spectral density across the input terminals. And I'm trying to figure out what value for that noise current spectral density creates that output spectral density Vn out squared. Okay, that's the goal here. So in order to make that happen, we need to know what the gain of the system is that converts that input current to that output voltage in general, right? So our small signal model on that end is going to look something like this, right? So we know that our gate terminal here is at ground, then we have resistor RG. Here's VGS. Now we're applying some input current. I'm just going to call it IN for the sake of argument. We don't have to carry around so many things. This is GM VGS. And here's our output voltage. And here's RD. So I would argue that by inspection here, we can see that V out is simply equal to IN times RD. Anybody have a problem with that? So by extension, we could say that Vn out squared is In in squared times RD squared. And therefore, In in squared is equal to Vn out divided by RD squared. We actually already solved for that way at the beginning. That was just our total current, all added together. So our input referred noise current is just what we found IN total to be earlier for this particular problem. Anybody have any questions, comments, or concerns regarding that?
Where did you say that IN total was from? Back, like a step one?
Between the source and the drain. Right? So all of that, so let's go back to that, right? Okay. Well, so between the source and the drain isn't really a good way to put it. Between the drain and ground. Right? Because a portion of it, literally the transistor current itself, IN-M1 is legitimately flowing from the drain to the source. The contribution of the resistor RG, once we refer it to the output side, so we multiply that noise voltage by the transconductance to give us a current flowing from the drain to the source, right? That current INRD, so the noise current generated by our resistor RD, is flowing between the drain and AC ground, where AC ground is the source. From a noise calculation perspective, right? Does that make sense? Yeah. So it should kind of make sense. Getting so confused saying sense, source, and all this kind of stuff so many times. But that's why we get this exact result. Let's work another one. Let's mess some stuff up a little bit. So we're going to look at a common source amplifier again, but we're going to mess it up by including feedback. We have some feedback resistor. F, I'm going to need to save this and restart. And here is where my input signal is taken. And again, we're going to look for VN in our input referred noise voltage. Input referred noise current, assuming that CLM body effects and 1/F noise can be neglected. So I have to remember not to write down the 1/F noise when I'm doing this. All right. Same basic steps, right? So for our noise analysis bit, let's see, we need to determine VN out where. So our noise analysis hinges on the fact that we've shorted out our input terminal here, okay? I'm making a note to point that out because for our small signal noise analysis, what's that going to do to that resistor RF? RF is going to be between the drain and a small signal ground, which is going to put it directly in parallel with that resistor RD. Okay. So effectively, what we would have is something that looks like this. And probably the easiest way to understand what's going on. Here's our resistor RD. Here is INRD. Here's our transistor M1, where our input is now at an AC ground. And here is the noise current generated by transistor M1. And then between the drain and ground, we're also going to have a resistor RF. And its associated current noise generator, INRF. And then here is where we will measure noise power output. Everybody okay with this representation of our circuit? Anything that makes sense? All right. So, since all of our noises are uncorrelated, we can lump them all together because they are all just current sources between the drain and small signal ground. So we can say that IN total in this case is INRD plus INRF plus INM1. And so that's going to be 4 kBT over RD plus 4 kBT over RF plus 4 kBT gamma. So I chose this problem specifically because even though there is a resistor that's tied to the gate for our amplifier model, we wind up getting a different representation of the noise because we're not referring it to the output. It's present at the output to begin with, right? So that's the difference between the last problem and this problem, like that RF is directly tied at the output. So we don't have to use the transconductance of the circuit to send that noise voltage to the output. We already get a noise current there. All right, so with that being said, what should our VN out be? Do we need to draw the small signal model, or do we have enough information to figure it out? So nobody's saying anything, which leads me to believe I might need to draw the small signal model. All right, so with our input voltage shorted, that means that our gate is at ground. Our source is at ground. Here we have GM, VGS. Between the drain and the source is where all of that noise current winds up flowing. So let's call that IN total. And then stop saying between the drain and the source. Between drain and ground would be a better representation. And we're going to see the resistor RD between the drain and ground. And we're also going to receive the resistor RF between the drain and ground. So I'm just going to call this guy RD in parallel with RF. Here is VN out quantity squared. So from this, VN out should be what? Exactly right. So 4 kBT RD plus 4 kBT over RF plus 4 kBT gamma GM, all multiplied by RD in parallel with RF quantity squared. All right, we only have 5 minutes left. So we'll pick up here on, what day of the week is today? Monday. We'll pick up here on Wednesday, finish up calculating the input referred noise voltage and input referred noise current. And then I think that's enough about noise out of me. Let's circle back around to getting back to figuring out how we're going to make an op amp. Now that we have what I hope to be a pretty reasonable understanding of what noise is. Single stage op amps, figuring out how we need to bias them, how we need to design them and all that kind of stuff should make a bit more sense now. All right, so we'll wrap this up on Wednesday, talk about differential pairs very briefly to move into that single stage op amp, which is just a differential pair loaded with a PMOS current mirror, so that we go from double ended output to single ended output, which is what we expect.